Hello again, and today's lecture is basically going to be on the second part of our Z transform series. So if we start observing some of the Z transform properties that we can see from this handout below, we can see basically there are 8 properties that we need to really be focusing on regards to Z transform. Of these 8 properties, the ones that we want to use the most, or are most popularly used, would be the shifting property, which you can see here. So the Z of negative n x of z. The reflection property, which is going to be x of 1 divided by z, and the convolution property, where x of n star x of n is going to be x of z multiplied by x of h of z here accordingly. So before we derive anything, let's start comparing certain properties. So the linearity property basically states that if we have any scalar components being multiplied in time to each one of these time signals, x1 of t and x2 of t, they also multiply accordingly to x1 of s and x2 of s. In the z domain, this also holds true, meaning that scalar properties are multiplied by x1 k of t and x2 k of t also transfers to x1 of z and x2 of z. The shifting property in the s domain is that if we had a shift of t minus t naught, this transfers to e to the negative s t naught x of s. In the z domain, this transfers such that the x signal here is shifted such that it's kt minus nt. We've also multiplied by a shifted unit step with the same delay, kt minus nt. And in the z domain, this represents a z to the negative n of x of z. For scaling, in the s domain, if we have a scalar multiple inside the brackets with t, this is going to be 1 on a multiplied by x s divided by a. In the z domain, it's just going to be a to the power of k multiplied by x of kt is going to be x of z divided by a. In the Laplace transform, when we watch it with respect to differentials, so we say tx of t, this is going to be negative dx of s all over d of s. In the z domain, if it's kx of kt, this is going to be negative z dx of z divided by d of z. So there are some similarities between the two transforms for s and z because of how the z complex coefficient is defined from the s complex coefficient that we saw in the previous lecture. So it's a less work to remember in general. So what about the dtft for an x of n sequence? That basically transforms say into x of capital omega. And the z transform for such a sequence we saw is basically when x of z is the summation series here in the yellow block. So the question we ask is when x of capital omega is going to be equal to x of z. So if z is equal to e to the power j capital omega, and we ask ourselves when or where is this going to be such that this exists, in the unit circle plot, this is basically going to be on the unit circle itself. So our dtft equivalent of x of n is given by the values of the equivalent z transform evaluated on the unit circle. One thing to note is that if the region of convergence does not include the unit circle, the dtft of x of n will never converge. So that just means that x of n will not have a dtft. And for our previous example, what we saw, we had the region of convergence of modulus of z going to be less than modulus of alpha. The dtft will not exist if alpha is less than 1. So the z transform can be expressed in this following polynomial form, where we start with a constant term here on the numerator, and we have descending powers of z, and then we have a constant term here of 1 on the we have a constant term here on the numerator, and we have descending powers of z, and we have a constant term here of 1 on the denominator, and then we also have descending powers of z. The familiar form for this is basically where we factorize the zeros here on the numerator and the powers here on the denominator, and we pull out a constant gain factor k. And this form is basically used to produce pole zero plots in the z-plane. So discretized time systems can be either represented by transfer functions, which look like this, impulse responses, which look like this, and difference equations, which look like this. So in particular, the ones we tend to use the most will be the transfer functions and the difference equations. So the output sequence y of nt, we can either find the inverse z transform here for this y of z signal in one of three ways. We can do long division, we can do complex integration, which we will not discuss in this course, and we can use partial fractions and tables. Long division is referred to as the infinite solution or the open form solution for x of z or y of z accordingly here in this slide. Partial fractions and tables refers to as the closed form solution or the finite solution for y of z. So please remember these terms accordingly, because depending on how the question is worded, it determines if you do long division or if you do partial fractions. A good enough hint is that if the question says you need to calculate up to a power of z, chances are that's going to be a long division question. If it does not say that, and it says something like closed form solution or finite solution, that's going to be partial fractions and tables. So for long division, before you actually do the long division, you need to make sure that y of z must be increasing powers of z to the -1. After that, you actually can perform the long division and get the answer. Now there's a supplementary lecture note on My Learning that shows you actually how to do the long division, so I advise that you actually download it and review it, so that way you actually have an idea how to do long division. We can also do a few of these problems in the tutorial classes as well, so we can get a hang of how to do long division as of such. We can also apply the shifting property of the z transform here in order to get the inverse representation, or if we just want it in terms of positive powers of z. So when we do this and we apply the shifting property here, we basically get our inverse z transform, and look how easy it is to do here. It's basically the 1.4 is going to just map onto delta of nt, the 0.94 here is going to be delta of n minus 1t, the 1.12 here, because it's z to the -2, is going to be n minus 2t, and so forth. And what this looks like, because of the sequence of values, is just basically a stem plot here. This is going to be n equals 0, n equals 1, n equals 2, and so forth. So long division gives us the sequence of values to produce a transfer function directly. And when the sequence doesn't end, in this case when we're doing long division, it's referred to as an infinite response. However, if we're doing long division and the sequence ends or converges to some value after some finite number of values, this is actually a finite response. The other technique that we're not really going to talk about too much is complex integration. And this basically is represented by a surface or contour integral here. And the technique to evaluate this is referred to as the method of residues. Please remember, we'll not be using complex integration in this course. The preferred technique for finding the finite solution, on the other hand, is using partial fractions. And this gives us the finite or closed form representation of the time sequence. So let's actually examine this. So the expression is basically said to be inverse transform, such that you need to actually observe this property here, where the degree of n of z must be less than the degree of d of z. If this property isn't observed, you need to long divide until this property is observed, and then you take the remainder divided by the original denominator and partial fraction only that part. So returning to our example here, we basically treat the z to the -1 here as our variable. And as such, we can partial fraction this accordingly. Because we have 3 factors on the denominator, that means we're going to have to solve for a, b, and c here, 3 factors accordingly, or 3 constants accordingly for each one of these 3 factors. So if we solve for a, we basically take the numerator that we had from before, and then we take the 2 factors here that a is not associated with, and put it on the denominator. And then we say for this factor here, which was a, we find out what the value is for this entire denominator here, of the value of z here, needs to go to, for this entire denominator to go to 0. Once we know this in this case, because it will be minus z to the negative 1 is equal to negative 1, so z to the negative 1 here is going to equal to positive 1, we substitute the z value here into this entire equation to solve for a constant. Similarly, we do the same thing for b here, where we use these two factors here that are associated with b and we put it on the denominator, and then we take the denominator of b here and we equate this to 0 and solve for z to the negative 1. And then we use this value of z to the negative 1 and we substitute it here into this entire equation to solve for b. And so forth for c. Finally, we get our a, b, and c constants here evaluated for y of z. Now, in checking the z transform tables, we can basically see that in this case the z transform table is represented in positive powers of z. But we can also delay this accordingly, so this will go back to 1 divided by 1 here minus z to the negative 1, and we can see it maps here accordingly to this transform. The other two transforms here map to this part in the z transform table. Okay, if we apply the delay property, we can basically see it's equivalent to this part here. So, in doing the inverse z transform, we actually get our answer here using the z transform tables. So this brings us to the end of our second z transform lecture.